If someone steals your encrypted data today, could a future quantum computer read it tomorrow? Start with a reality check. Your bank logins, medical records, and software updates rely on math-based locks. Quantum computers use physics, not faster CPUs, to attack some of those locks. That creates a new risk. Attackers can harvest encrypted traffic now and wait. This video maps the concrete steps to protect your data. From what's actually broken to what you should change today, starting with how quantum machines think. Quantum machines compute with qubits instead of bits. A single qubit can represent multiple states at once. That's superposition. Multiple qubits can become entangled, so measuring one affects the others instantly. Algorithms exploit interference to amplify correct answers and cancel wrong ones. Think of it as many hikers exploring a maze simultaneously. Then a signal boosts the correct path. That strange behavior lets quantum algorithms tackle specific math problems far faster than classical computers. Not every problem gets faster on a quantum computer. Advantage is algorithm-specific. Researchers call today's machines noisy. Qubits make errors and need correction. Building error-corrected logical qubits costs huge hardware overhead. So we're not at instant crypto collapse. But progress is steady. Roadmaps from major labs aim to scale qubit quality and count. The key question becomes timing. When will quantum hardware be good enough to threaten real-world keys? Shor's algorithm is the headline threat. It finds structure in numbers that classical methods struggle with. Practically, that means factoring large primes and solving discrete logs quickly. Those math problems underpin RSA and many elliptic curve schemes. If an attacker runs Shor on a powerful, error-corrected quantum computer, they can recover private keys and impersonate sites, forge signatures, and decrypt captured traffic. But how many qubits would that actually take? Grover's algorithm is different and less dramatic. It speeds up brute force search by roughly a square root factor. For symmetric ciphers, that effectively halves security bits. AES 128 would feel like AES 64 under Grover. The practical fix is simple. Use longer keys, like AES 256, and strong hashes such as SHA 256. So symmetric crypto survives with parameter changes, while public key systems face a structural break. So where do we go from here? NIST ran an open competition to evaluate dozens of PQC candidates. After years of study, NIST selected leading algorithms and published draft standards. That process mirrors how AES and SHA were chosen decades ago. Standardization matters because TLS, VPNs, and PKI all rely on stable, vetted primitives. With drafts out, vendors are testing implementations. But adoption will take planning, testing, and PKI updates. So what are the frontrunners you'll hear about? 3 names come up most: Kyber for key exchange, dilithium for signatures, and SPHINS as a conservative hash-based option. Kyber offers efficient key establishment. Dilithium balances speed and compact signatures. SPHINS is larger but conservative. Each choice trades size, speed, and implementation complexity. Expect certificate sizes to grow and handshake messages to expand. Browsers and CDNs already ran hybrid tests. How those trade-offs play in your environment will determine your migration path. Performance matters in production. PQC keys and signatures are often larger than their classical counterparts. Some schemes sign slower, others verify fast. Implementations also need side-channel protections. For web traffic, CDNs and browsers report manageable overheads for hybrid handshakes. For embedded devices and IoT, the overhead can be painful. That creates a migration puzzle: where to pilot first, and how to measure user impact and MTU problems before a full rollout. Hardware progress is real but uneven. Labs have built hundreds to thousands of physical qubits, but quality trumps quantity. Breaking RSA 2048 likely needs millions of high-quality physical qubits and robust error correction. Estimates vary. Many experts say a decade or more. Yet adversaries can record traffic now and wait. That mismatch between hardware timelines and data lifetimes is why agencies urge action today. So how do attackers exploit that waiting period? Harvest now, decrypt later is the clearest threat model. Attackers capture encrypted traffic today, archive it, then decrypt once they possess a CRQC, cryptographically relevant quantum computer. Sensitive records with long confidentiality requirements are most at risk. Think health data, classified archives, and intellectual property. Use a simple formula: confidentiality lifetime plus migration time versus time to CRQC. If lifetime exceeds the expected CRQC arrival, migrate now. Next, what practical steps should organizations take first? Step 1. Build a cryptographic inventory. List every place you use crypto: TLS endpoints, VPNs, SSH, code signing, backups, HSMs, mobile apps, and embedded firmware. Record libraries, curve choices, key sizes, and certificate chains. Don't forget third-party components and supply chain links. An accurate inventory reveals where your longest-lived secrets sit and where migration will be hardest. With that inventory, you can classify data by confidentiality lifetime and exposure, which brings us to prioritization. Prioritize by exposure and lifetime. Internet-facing services and code signing deserve top priority. Long retention archives, medical records, and IoT firmware follow. Supply chain hotspots like update servers and device provisioning are high risk. Create a risk matrix that pairs data lifetime with exploit impact. That matrix tells you where to pilot PQC and hybrid handshakes first. But vendors matter too. So next, demand crypto agility from your suppliers and cloud partners. Demand PQC readiness from vendors. Ask for hybrid key exchange support, PQC-ready libraries, and migration roadmaps. Require testing evidence on performance and side-channel mitigations. Make larger certificate sizes and explicit compatibility check. Include PQC clauses in procurement and SLAs. Vendors who can't answer need roadmaps and deadlines. While you push vendors, you should run your own tests, starting with hybrid TLS handshakes in a controlled environment to observe real behavior and failure modes. Run hybrid deployments as your safety net. Pair a classical algorithm like X25519 with Kyber during TLS handshakes. That preserves classical assurances while adding post-quantum resistance. Measure handshake size, CPU cost, and middle box interactions. Document compatibility issues with load balancers and legacy firewalls. Use limited pilots, internal services, dev environments, or partner links. Capture telemetry to guide broader rollouts. After pilots, update PKI and key management to accept larger certificates and new object types. Update PKI and key lifecycles. Prepare your CA to issue PQC or hybrid certificates when standards finalize. Shorten key lifetimes where possible to reduce exposure. Revise rotation policies and ensure HSMs support new algorithms. Document everything for audits and supply chain partners. Training matters too. Educate developers, SREs, and security teams on new libraries, signature formats. And common pitfalls. People often underestimate the human work behind crypto migrations, which leads into an often overlooked problem space: embedded devices and IoT. What about quantum key distribution? QKD sends keys using quantum optics and offers interesting guarantees for point-to-point links. But it needs special hardware, dedicated fiber, and new trust models. It won't replace PQC across the internet. Use QKD for specialized, high-assurance links if it fits your threat model. For broad, scalable protection, software-based PQC is the pragmatic path. That clears up common myths and false comforts, which we'll debunk next. Myths versus facts. Quantum won't break everything overnight. Symmetric crypto survives with larger keys. You shouldn't wait for a breakthrough to start migrating. PQC runs on classical hardware today, and QKD is not a panacea for internet-scale problems. The real risk comes from delayed action and long-lived data. Migration is multi-year and multidisciplinary. So what does a practical, phased timeline look like for organizations ready to act? A phased timeline works. Now, inventory, vendor engagement, and pilots. In 12 to 24 months, adopt NIST-approved options as standards finalize. Update PKI, and broaden deployments. Continuously, rotate keys, reissue certificates, and maintain training. Track NIST, CISA, and IETF guidance. The organizations that start early avoid a frantic, expensive scramble later. Here's a compact, practical checklist of immediate actions to protect your long-lived secrets right now. Quick checklist. Inventory your crypto. Classify data by retention. Prioritize internet-facing and signing systems. Demand PQC readiness from vendors. Pilot hybrid handshakes. Update PKI and HSMs, and run embedded device audits. Avoid homegrown crypto. Keep hybrids during the transition. Harden implementations against timing and cache attacks. Document every change for audits and partners. Start small, measure impact, then scale. Do this and you'll be ready when standards finalize and mandates arrive. To wrap up, quantum will eventually break many public key systems, but you can control the timeline. Act now if your data must stay secret for decades. Build an inventory, pilot PQC hybrids, pressure vendors, and update PKI. The work is routine engineering, not science fiction. Start these projects now, and you'll avoid emergency migrations under regulatory deadlines. If you want a downloadable starter checklist and sample vendor questionnaire, I've linked one below. So what should you ask vendors first? If this helped, like the video and subscribe for practical security guides. Comment what systems you need a checklist for, and I'll make a follow-up template.